I am K.Anita Davamani, Assistant Professor, Department of Computer Science and Engineering in Bharat Institute of Higher Education and Research. In this course, Artificial Intelligence, we are going to see about the topic searching strategy. The agenda for this session is what is searching strategy, types of searching strategy, search algorithms, breadth first search algorithm, example of DFS, depth first search algorithm, and example of DFS. First, we have to see about searching strategies. We have to know what is searching. Searching means it is a process that is used to find the solution for a given set of problems. Here we are having two ways of searching strategies. First one is uninformed searching strategy and second one is informed searching strategies. First, we have to know what is uninformed and what is informed. Uninformed search strategy means no information will be provided regarding the given set of problems, or we will not be having any domain knowledge related to the given problem. That is called as uninformed search. Because of this reason, it is also called as blind search. And the second one is informed search strategies. So here we will be having a domain knowledge about the given set of problems. So this particular searching strategy is also called as heuristic search. Now we will see the difference between informed search and uninformed search. So informed search means already I told you that we'll be having a domain knowledge. So it uses knowledge for the searching process. But uninformed search will not be having any knowledge about the given problem. So it does not use knowledge for searching process. Informed search finds solution more quickly because it is having information about the given problem. Uninformed search, it finds solution slow as compared to the informed search. And informed search is highly efficient, but uninformed search mandatory efficient. And cost for informed search is low and cost for uninformed search is high. And also the informed search consumes less memory and uninformed search consumes moderate memory and also time. So because of this, compared to uninformed search, informed search is better in time and space complexity. So these are the search algorithms. Here we are having number of algorithms under uninformed and informed searches. Under uninformed search, we are having breadth first search algorithm, uniform cost search, depth first search, depth limited search, iterative deeping depth first search, bidirectional search. And under informed search algorithm, we are having best first search and A-star search. So here today, we are going to see about breadth first search and depth first search in this session. First, we will see about breadth first search. It is the most common search strategy we can use for trees as well as graphs. Because of this nature, it searches breadth-wise. It is called as breadth first search. And also the search starts from the root and expands to all successor nodes of the same level. After completing the current level, it will move to the next level of search. And for this particular implementation, we can use first in, first out queue. The time complexity and the space complexity of breadth first search are the same, that is big O of n power t. Advantages and disadvantages of breadth first search. Breadth first search is complete and we can able to find out the optimal solution for the given problem. Disadvantages, it occupies a lot of memory space. Because of this, the time to execute the particular given problem or given search is high compared to the informed search. Because if the solution is at the bottom or end of the tree, means we have to store a lot of elements in the FIFO queue. So see, this is the example tree structure. Here we are having 4 levels, that is, 5 levels from 0 to 4. We will start in the root node S and we have to progress through the next level, that is the node A. After visiting the node A, it should move to the adjacent node B. So after completing the level 1 nodes, it should move to the next level C. So like this way only it will search and it will find out the solution for the given problem. This is the algorithm for birth first search. So in this algorithm, what we have to do is first we have to mark all the vertices as not visited. After that, we have to create a queue for birth first search. And whenever we are visiting a node, the node should be enqueued inside the FIFO queue. And after visiting the node, we have to dequeue and we have to find out the adjacent nodes of the current vertex. Like this way, we have to search one by one node that is given for us. This is the example. So I have taken graph example for breadth first search. And here we are having node A to node H. So how we are going to traverse this particular graph? That is the problem given to us. So initially we will be having a graph and also FIFO queue. Initially we marked all vertices as not visited. So now we are going to check for the node A. So now we are in node A. So we have to enqueue the source node A into the FIFO queue. So now we are having node A inside the FIFO queue. Next, we have to dequeue the vertex that is available in the FIFO queue. And we have to find out the adjacent vertices or neighbor vertices for A. So what we have to do when we are dequeuing the next vertex, I have marked the color of that particular vertex as red to identify which node we are going to work. So here A is marked as red and we are going to visit the neighbors of A. Here what are the neighbors of A? Node B and node I. See, node B is a neighbor of A. So what we have to do? We found or we discovered B. So we have to put B inside the FIFO queue. Next one is we have to visit the next neighbor node. That is I. So now what we have to do? We discovered I and we have to put I inside the FIFO queue. Now what are all the elements we are having inside the FIFO queue? We are having node B and node I. Now we can mark the node A as visited, that is finished. So now we have to move to the next node. Next node is node B is in the front of FIFO queue. So what we have to do? We have to dequeue the next vertex from FIFO queue. So we have to dequeue B. B is in the front. So we have to dequeue the vertex B and we have to mark B in red color to identify its neighbor nodes. So now we are going to visit the neighbor nodes of B. So now what are the neighbor nodes of B? Here F is a neighbor node for B. So what we have to do? We have to put F inside the FIFO queue. So F is discovered. So we have to enqueue it inside the FIFO queue. So next node is A. We know that A is already discovered. So we can leave it and we have to take care of the next process. So next what we have to do? What is the next vertex we are having in the FIFO queue at front? So here we are having I. So what we will do? We have to dequeue the next vertex from the FIFO queue. So we have to dequeue I and mark the I in red color to identify the neighbors of I. So here, what are the neighbors of I? A is a neighbor for I, but we know A is already discovered. So we can leave A node and we have to check for the next node. What is the next node? Next node is E. E is a new node. So what we have to do? It is discovered and we have to NQ it inside the FIFO queue. So next one is what we are going to do. Again, we are going to visit the next neighbor of I. So what is that? F is a next neighbor and F is already inside the FIFO queue. So no need to take it. So now F already discovered, so no need to take it. And what we have to do? I is finished. Now we have to check inside the FIFO queue. What is at the front of FIFO queue? So F is at the front. So what we have to do? We have to DQ F node and we have to mark it in red color to identify the neighbors or adjacent nodes of F. So here what are the adjacent nodes of F? B is there, E is there and I is there. So already we know B is discovered already, I is also discovered and E is already inside the FIFO queue. And what is the next node? Next one is G. G is also neighbor for F. So what we have to do? We have to discover the node G and NQ it inside the FIFO queue. So next what we have to do is now F is completed, that is F we finish, and we have to check for the FIFO queue what node is at front. So here E node is at front. We have to DQ the node E and we have to mark it in red color to identify the neighbors of E. So what are the neighbors of E? I is neighbor for E and F is also a neighbor for E. And we know E is already completed because I and F are already discovered. So we can leave it. And again, we have to check for the FIFO queue what is at the front. So now node G is at front. So what we have to do? We have to DQ the node G and we are going to mark it with a red color. So what is there now after G node? What we are going to do? Just we are going to check the neighbors of node G. What are the neighbors of node G? Node F, node C. Okay, node F is already discovered, so no need to take it up. So what we are going to do is we are going to NQ the node C inside the FIFO queue. So after that we have to check for the next neighbor, that is H. H is also a new node and we discovered H and we have to put inside the FIFO queue. So now the neighbors of G is finished. So now we have to check the FIFO queue for the next vertex. So what is at the front of FIFO queue? C is at the front of FIFO queue. So we have to DQ the next vertex and we have to mark it in red color to identify the neighbors of node C. So now check what are the neighbors. G is a neighbor, H is a neighbor and also D is a neighbor. So what we will do? We have to discover the unvisited nodes. So D is unvisited node. So we have to NQ D inside the FIFO queue. Now what we are going to do? We have to check what is there at the front of FIFO queue. So we have to get that vertex, that is H. We have to take our, we have to DQ the vertex H and we are going to mark it as red color and we are going to find the neighbor nodes of H. So check what are the neighbor nodes of H. G is a neighbor node and also C is a neighbor node. So both are finished already. So we have to move to the next vertex, what is at front of FIFO queue. So here we are having node D. So now we are going to DQ the node D and we are going to check for its neighbor node. So the neighbor node is C. C is the neighbor node for D. And we know that already C is visited. And what we are going to do? We are going to start the process because we visited all the nodes that is available in the given graph. So like this way only breadth first search will work. It is very easy. And now we are going to see about the depth first search. This is the next search algorithm we are going to see. So depth first search is also like breadth first search, BFS only. This algorithm starts with the initial node of the graph G, and then it will goes to deeper and deeper until we find the goal node. Okay, so not like BFS. In BFS, we will move. How we will move? We will move from level 0 to level 1. After completing the level 1 only, we can able to move to the level 2. But depth first search is not like that. Initially, it will start with the level 0 and it will go to deeper and deeper until we find the goal node or the node which has no children. So this algorithm then backtracks from the dead end towards the most recent node that is yet to completely unexplored or unvisited. So here we have to use stack data structure, that is last in first out. In the breadth first search, we work with the FIFO, that is first in first out queue. But in depth first search, we are going to use the stack data structure to the implementation process. And this is also similar to breadth first search algorithm. Here, the edges that leads to the unvisited node that are called discovery edges, while the edges that leads to an already visited node are called block edges. So yet to visit are called discovery edges. Already visited nodes are called blocked edges. This only we have to remember when seeing the depth first search. This is the algorithm. So in the first step, we have to set the status of the given graph as 1. We have to set the status 1. So that means the graph is in ready state. In step 2, we have to push the starting node of the given graph on the stack, and we have to set it status is equal to 2. That is waiting state. In step 3, we have to repeat the steps 4 and 5 until stack is empty. So see, in step 4, what we are having, we have to pop the top node from the stack and we have to mark the status as 3. That is processed state. And in the step 5, we are going to push on the stack all the neighbor nodes of the currently pop out node. So at that time, what we are going to do is we have to set that particular neighbor node status as 2, that is waiting state. So that is end of loop and we can exit the algorithm. So check here, I have given one graph example. So consider this graph G along with its adjacency list. So here I have given the adjacency list. If it is not given, first we have to find out the adjacency list for the given nodes. So here we are having nodes A, B, C, D, E, F, G and H. So we have to find out the adjacency list for all these nodes. So here see, so what are all the, here it is the graph given is directed graph. So it is quite easy for us to identify the adjacency list. So first we will see the adjacency list for A. What are the adjacent vertices for A? So that is node B and node D. So we have to find out the adjacency list for B, that is node C and node F. So like this, we have to find out the adjacency list for all the given nodes. So that is given in this side. So after this, what we are going to do is we are going to start our solution. So how we are going to visit this graph? So initially, we are going to start with the node H. We are going to start with the node H. So what we will do, we have to push the node H onto the stack. So now what the stack will be having, H will be on the top of the stack. So now what we are going to do? We are going to pop that element that is available in the top of the stack. So what will be there in the top? H will be there in the top. So when we are popping up the element, we have to print that element H. So now what we will do? We have to check for the neighbors of H. What is neighbor of H, or what is adjacency list that is given for H? That is A. So A is the neighbor. So what we have to do? We have to push the neighbor of H inside the stack. So now the stack will have the node A. So after that, we have to pop the stack, pop the top element of stack out, and we have to print it and push all the neighbors of A inside the stack. I'll tell this once again. Here we are seeing about the depth first search. Okay. So initially I told you that we have to check the adjacency list for each and every node in the graph. That we have done already. Okay. So what we will do initially, we have to push the starting node onto the stack. So what is the starting node here? H is the starting node. So we push H onto the stack. Okay. So now what is that in the stack? H we are having inside the stack. Okay. After pushing the node H into the stack, we have to pop the top element. So now we are having only one element inside the stack, that is H. So we have to pop the H and we have to print H. Okay. So then what we have to do? We have to check for the neighbor nodes of H. What is the neighbor node of H? Here we are having the adjacency list. So now neighbor node of H is A. A is the neighbor node. So what we have to do? We have to push A inside the stack. Okay. Now A element will be there in the top of the stack. So what we have to do? Again, we have to pop the element A and we have to print it. Okay. So after that, we have to check for the neighbor nodes of A. So we have to check the adjacency list again. So what are the neighbor nodes of A? Here B and D are there. Okay. So what we will do? We have to push B and D inside the stack. Okay. So first we will push B and second we will push D. Okay. So now we know that stack means that is last in first out. So what we pushed last? D. So when popping out the element, we have to pop the top of the element. What will be there in the top of the stack? D. Okay. So what we have to do? We have to print D, and after that we have to check for the neighbors of D. So after popping D, we will be having only B inside the stack. Now the top value of stack is B. Okay. After this, what we have to do? We have to check for the neighbors of D. Again, we have to check the adjacency list that is given. Okay. So what is the neighbor for D? The neighbor for D is F. What we will do? Already we are having the element B inside the stack. Again, we are going to push the node F inside the stack. Now the top value will change from B to F. This already we know and we studied in the stack data structures. Okay. Okay. Here what we will do now, the top of the stack is F. So what we have to do? We have to pop the top element. What is in the top? F. So we will print F and we have to check the neighbor nodes or adjacency node for F. Okay. Again, we have to check the adjacency list. Okay. So what is there for adjacency of F? Adjacency of F is A. And we know already node A is in the waiting state, that is already visited. So what we have to do, we can leave that node. No need to push it inside the stack because already it is visited. Okay, so what is there in the top of the stack now? That is stack B, element B, or node B is there. So now what we have to do, we have to pop the top of the stack. Okay, so when we are popping the top value, we have to print the element first. Okay, print B. After that, we have to check for the neighbor nodes of B. Okay, now again we have to check the adjacency list. So what are the elements we are having in the adjacency list of B? Elements C and F. Okay, node C and F. What we will do in this case, already F we printed. Okay, so now what we have to do, only C we have to push it inside the top of the stack. Okay, so after pushing it, what we will do, we will pop the top of the stack. So we are having only one element inside the stack, that is C, and here we are going to pop out the element C. Okay, and what we will do, we have to print C, and after printing C, we have to check for the adjacency list. Okay, for identify the neighbor nodes of C. Okay, so now again we will check neighbor nodes of C. What are the neighbor nodes of C? Element E, that is node E, node G and node H. Here we are having 3 nodes are neighbor to node C. So what we will do, what are all the nodes? That is E, G and H. H already visited. Initially we visited H. So we can leave that H. So what we will do in this case, we have to push E and G inside the stack. Okay. Now what will be in the top of the stack? G, because last in first out. Okay. So what we will do, we have to print G and we have to pop the element G out from the stack. Okay. So after taking out G from the top of the stack, the stack will be having only E. Okay, and what we have to do, we have to check for the neighbor nodes of G. Okay, we have to check for the neighbor nodes of G. So now we will check the adjacency list, that is E and H. Already E is in the E and H is already visited. Okay, so E and H is already visited. So what we will do, just will print E, and what we have to check, any node is there inside the stack or not. No node is there inside the stack because we have visited each and every node that is given inside this. Okay, so now stack is empty. We are not having any nodes inside the stack or any element inside the top of the stack. So what it means? It means we have been traversed all the nodes that is given in the graph. Okay, finally, what we have to do, we have to print the sequence of the graph. Okay, so how we have to print? So what are all the things we have printed? So first H. Okay, so first we have to print HCH. So next what we printed? Next we printed A. Okay, so next node is A. Okay, so the next node is D. After A, we printed D. Okay. So after that, we printed F. After D, we printed F. Then check after F, we printed what we have printed. We printed B. Okay. After F, B. And what we are having after B, we printed C. After C, we printed the node G. And after node G, we printed E. So now check the given graph whether we have traversed all the nodes. H node we visited initially, A, B we visited, C we visited, all the nodes that is given in the graph we visited. Okay, so this sequence is the traversal sequence for the depth first search. Okay, so here it is very important for us to remember only one thing, that is we have to know how to identify the adjacency list for the given graph. Okay, so the given graph should be directed graph. So it's quite easy for us to identify the adjacency list for the directed graph. So easily we identify the adjacency list for the given graph. Okay, so only one thing we have to remember in the birth first search and depth first search, that is in birth first search we are going to use the first in first out queue, that is FIFO queue for the implementation. And in depth first search what we use? LIFO stack, last in first out stack. So this is the major difference between birth first search and depth first search. Okay, so here in birth first search what we did, we have to search for the element level by level. Okay, after completing one level only we can move to the next level, but not like that. In this depth first tree we have to go deeper and deeper until we find the goal node in the given graph RT, that tree. That is the major difference. Okay, so this is the difference between depth first tree search and birth first search. Hope you people are able to understand this.